Hello, Sid2 here. Let's talk about thermal mass. Now, people often get thermal mass and thermal insulation confused, and that's completely understandable because they both help to control how heat transfers into and out of our home, and they can both help keep our home cooler in summer and warmer in winter. However, thermal mass and thermal insulation have very different properties and work in different ways. So it's important to understand the difference between these two so that you can use them to full effect to improve the performance of your home. The simplest definition that I've been able to come up with for thermal mass is the ability of a material to retain and release heat over time. Now this may sound very similar to thermal insulation. However, insulation works by resisting the flow of heat from one side of a material to another, be it from outside to inside during summer and from inside to outside during winter. So it's using a different property of the material in order to achieve a similar result in terms of controlling the flow of heat energy. Materials with a high level of thermal mass work a bit like a thermal battery in that they have the ability to store and retain heat that's absorbed from the external environment, such as from the sun, and then they release this heat at a later time, hopefully when it serves a useful purpose, such as warming a room after the sun has set. Thermal mass can also be beneficial in summer by helping to regulate the internal temperature of a building and to smooth out the fluctuations that are occurring in the external environment temperature. However, you have to be careful with thermal mass in summer because that retained heat that helps to regulate the temperature during the day can then be released later at night and cause our buildings to overheat. This retained heat then needs to be flushed out of a building at night in order to prevent internal spaces from overheating. There are typically 4 physical properties of a material that we look at in order to evaluate how much thermal mass a particular material has. These are density, thickness, time lag, and decrement factor. Density refers to the mass of a substance or material per unit volume. In other words, the more closely packed the molecules are that make up a material, the higher the density of that material. Generally speaking, materials that have a high density will also have a high level of thermal mass. Some common building materials that have a high level of thermal mass include concrete, brick, plasterboard, and fiber cement. Thickness refers to the thickness or width of a material. And this is important because the thicker the material and the more dense the material, the higher the level of thermal mass. So before I mentioned that plasterboard and fiber cement are materials with a high level of thermal mass. That is true. However, they tend to be very thin materials. Plasterboard is typically 10 millimeters. Fiber cement varies in thickness from 6 to 12 or 18 millimeters in thickness. And so the thickness also has an impact on the amount of thermal mass that may be available. The greater the density and the thicker a building material happens to be, then influences the time lag. It's measured in hours, and basically it's the number of hours it takes for heat to transfer from one side of the building material to another. It's this time shift or delay in the heat transfer through a building material with high thermal mass that helps to regulate the internal temperatures of our building. Lastly, there's decrement factor, which refers to the ratio of average daily heat flow through a material compared to an imaginary material with zero mass. Now this can be a bit difficult to get your head around. If a building material has a decrement factor of 1, this means that 100% of the heat that it's exposed to throughout the day will transfer through that material. Basically means it has very limited thermal capacity. If a building material has a decrement factor of 0.5, this means that 50% of the daily heat that it's exposed to will flow through that material, while 50% of the heat will be retained by that material. So it has a medium level of thermal capacity. Generally speaking, materials with a low decrement factor will perform better as thermal mass. In this table, you can see some common building materials with their thickness, density, time lag, and decrement factor. Take, for example, 10mm plasterboard. It's a reasonably dense material, but because it's quite thin, you can see that the time lag is quite low and the decrement factor is quite high. Then we start getting into materials such as brickwork, and you can see there that it's a more dense material, and because we've now got a bit of thickness to the material, the time lag has increased substantially, as well as the decrement factor has gone down. And then there's concrete, which is my preferred way of integrating thermal mass into the design of a building. It has a high density, an increase in time lag, and it also has a lower decrement factor. Now, it can be quite difficult to work out some of these values and properties of a building material. Density and thickness are quite easy to determine. However, things like the decrement factor and the time lag require some quite sophisticated calculations. You'll also find that many building materials aren't used in isolation. They're part of an assembly or a combination of different materials, and then you have to calculate the time lag and decrement factor for all of those different materials and then convert them into a single value. Thankfully, energy analysis tools such as CHINATH and NatHERS do all of these calculations for us and can take into account the impact they will have on the thermal performance of a building. If you have a look at my website, you'll find some examples of different types of constructions and building materials, along with their different thermal performance values, and some advice on how you can integrate them into the design of your building. Thanks for watching. I hope you found this information valuable and easy to understand. There's links in the description below for some of the things that I've talked about in this video. And if you liked it, please subscribe, and I'll catch you next time.